And we dealt with the most familiar of all titration curves, the one you will most often see. That is a strong acid titrated by a strong base. This is what we've done. And we're on page 94 in your acid-base book. And you will remember that at the beginning, man, I made a mess of this thing, scribbling all over it. There we go. At the beginning, in this section here, we have excess what? Acid. And then what is happening here? Neutralization is complete. Okay? During that, like there's like, you add one single drop and base of the NaOH, like hardly any volume, and it tips the scale from being, oh, we were acidic to, boom, oh, we're basic. Yes. I believe so, yes. Yeah. Yeah. And so what's happening is you're going from, essentially you're like, all of a sudden I have no acid, and then I go to having some base. So it's like I have some acid, some acid, some acid, some acid, no acid, and then base, right? So it's like just jumping up crazy. Yeah. Okay. And then up top.
Good morning, Lindsay Mountain. Sorry for this interruption. We are here to announce the Phone Free Friday winners. They are Matilda O'Donoghue, Sammy Tang, Isla Timchak, Jaden Longmore, Zaid Amirov, and Xavier Faria. We will come by your classroom shortly. Thank you.
Okay, so, and then at the top we have excess base. Do you remember what species we have here? Does anyone other than Jude remember? Salt and water. We have the salt and the water. And the reason that it is pH 7, what is true about the salt and its ions that makes it pH 7? Yes? They are neither acids nor bases. Neither of the ions hydrolyze. Okay, moving right along now. No. Oh, that's dreadful. Okay. Where are we? 77. Oh my freaking God. There we go. Okay, what does this look like? What do you imagine we have titrated here? What's in our flask? No, don't talk about other things. What's in the flask?
Water. Base.
It's starting out basic, so in the flask we have a base. And what are we adding to it? Acid. Okay, this is a strong, because it's got that shape. It's kind of like mostly flat, but a little downhill, right? Or is this, that's downhill for you guys. And then vertical, and then, and it's still got that salt at the equivalence point. There's not much else to it. It's just, there we are. Okay. So HCl is the titrant, NaOH is the analyte. Now we get into the one where we have actual different stuff happening. So our analyte, in this case, is a weak acid. It is CH3COOH. And the titrant is a strong base, sodium hydroxide, NaOH. So if our analyte is now a weak acid, what would the initial pH be like? Compared to a strong acid, strong base titration. So if we have a weak acid, as analyte instead of a strong acid, what will the pH be like? Let people think. Tell your partner. Okay, yes, it will be less low. It will be higher. Why will it be higher? Because it's a weak acid. Okay, so here's point number 1. That's not pH 1. That's point number 1, point number 2, point number 3, point number 4. So at point number 1, we have all acid. At point number 2, what have we reached at point number 2? We have reached neutralization is occurring. I mean, it's not occurring, it's completed. As we swing, and you see that volume, it just goes all the way. It's 50 milliliters the whole way up, okay? What do you notice about the equivalence point? Yeah, the pH is greater than 7. Please explain to your partner why you think that might be.
So when there is equal one, there will also be CH3COO minus.
Talk quieter. That way other people can think for themselves instead of just eavesdropping.
This is a weak base.
All right, Mr. Elliott Clark, what do you have to say for yourself?
So because CH3COO minus is a base.
Yep.
Like that. And therefore, so the leftover at the equivalent point, it will eat up some of the plus ions, and then it would be a base.
Okay, that was kind of correct. The parts I was not so keen on were there will be some of that left over, because it's not that there's, I don't know if you use the word leftover, I might be like projecting that. It's not that there's going to be some of it, it is that the acid, the original acid and base are now all gone at the equivalence point. And this is all we've got. I mean, we have water as well, but that's not very exciting. So it has been 100% converted to salt plus water at the equivalence point. Could you please, somewhere, maybe here, write the equation that shows how these products here make the solution basic? Write the equation that shows how this product here makes the solution basic. Does that look like what you have written? Yeah? Okay, good. All right, let's see what this has to say here. So at point number 1, no NaOH has been added yet, so the pH is low. But since acetic acid is weak acid, it is only partially dissociated, so there is less H3O plus than when we had HCl. Okay. Between points 1 and 2, as NaOH is added dropwise, the H3O plus slowly starts getting consumed by the OH minus. The analyte is still acidic due to the unreacted H3O plus. Now, one thing I want you to notice here is that the graph starts with a little hill. Starts with a little hill. Did a strong acid, strong base start with a little hill? No. And then we have this zone here where we have steady, shallow increase. Yes?
Why does it start with that?
Yeah,
Just does.
it does.
All right.
I think I could think my way through it if it weren't early in the morning, but it kind of, well, I guess it's not that early in the morning, but
It's early.
yeah, I feel like I think through this every year, and every year I'm unsatisfied with what I come up with. So probably what I come up with will not satisfy you. If you want to find out, you can go Google that. Is good? Okay. All right, so there's a little hill, and then it's steady and shallow, and this zone in here What species are present in between point 1 and point 2? Na is present. Ooh, I'm going to add something onto that. What species are present that affect the pH? Because Na does not affect the pH, so we're just going to leave that alone. Uh-huh. We have CH3, COO. What do we want on the end there? Minus. Anything else? CH3, COOH. If we have those two things, what do we have? There's always hydronium and hydroxide because they're present in the water. Elliot? Yeah, we got H+, but that's always present. H+ is always present. OH- is always present. Nathan? We have an equilibrium. We have a weak acid and we have its conjugate base. That's one word. We have weak acid. We have the conjugate base in equilibrium with each other. Yes, we have a buffer.
You are tremendous.
Right, because we have a weak acid, we have its conjugate base, so we have a buffer. Now, where would this buffer, where in the titration curve would we have the best buffer? I don't understand why you're not talking amongst yourselves. Talk amongst yourselves. Go, 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 go. Where would we have the best buffer in that blue area between point 1 and point 2? Oh.
Oh, actually. A little under what was not allowed. We made it over. We made it.
Where would we have the best buffer solution? Approaching point 2 where? Like near point 1, in the middle, or near point 2? Near point 2? No, but you weren't here last week, so we'll forgive you. All right, Elliot.
At the half equivalence point?
At the half equivalence point, why is that the best buffer?
Because there's a whole amount of
At the half equivalence point, what do we have? We have equal amounts concentration of HA and concentration of A minus. And when do you have the most effective buffer? When you have lots of the weak acid and lots of the weak base. So that's why it's the best, is because we got the most of each kind of in balance with one another. Remind me, how would you find the pH at the half equivalence point? Actually, remind your partner, how would you find pH at the half equivalence point?
Are you serious?
Okay, pH at the half equivalence point is pKa. Yes. Excellent. Okay. And then, of course, we've got the equivalence point. We talked about that. What was the pH? It was, what, that looks to be about, what, 8.2 or so? Yeah? We can fill this in even though we already did it. Who are the ions in NaCH3COO? That was the salt. Never mind. Na plus. And CH3COO minus. Does Na plus hydrolyze? No. Does CH3COO minus hydrolyze? Yes. We already wrote the equation, so I'm not going to have you write it now. Is the solution acidic, basic, or neutral? It is. Okay, write the hydrolysis equation again.
Okay, we're coming here now.
Is good? Can we move on? Okay. I don't know what's happening over here, but now after the equivalence point, what's happening after the equivalence point? Who is affecting the pH here? Yes?
Hydroxide ion. From NaOH.
The hydroxide ion from NaOH. Are there any other species present that could, in theory, affect the pH? Pardon me? The ion. CH3COO minus is present, but what? It produces negligible amounts of OH compared with the sodium hydroxide. Excellent. Now, just before we carry on to our next thing, I would like you guys, once you've finished writing down any of that, just on a piece of paper anywhere, okay? Scrap paper, so if you need some scrap paper, go grab some scrap paper. I would like you to try drawing the titration of a weak base with a strong acid. Let's assume our weak base is 0.1 molar, okay?
Wait, I'm scrolling up on the yeah, but I'm just scrolling up to see what. I watch all of other people rarely. And they say some bad about they see some bad about correlation. And then November 12th.
How are we doing? Are we done? Who's done? Half of you. Okay. We'll give the rest of you time to finish. Some people are being more meticulous than others.
Yes.
Mm-hmm. It's all good.
Ask my boy Rick, bro. Add my coon Rick, bro.
All right, friends, where should we be starting? How high? Ish. How high-ish? There's definitely a number that you can say, oh, we should definitely be above or below. We're above 7, that's for sure. Is there anything we should be below if we're at 0.1 molar? We should be below 13. Why? If we had a strong base at 0.1 molar, then our POH would be equal to, this is 10 to the negative 1. Our POH would be equal to 1, so our pH would be equal to 13. We now have a weak base, so our initial pH should be less than 13, because 13 would be for a strong base. So it would be less than 13 and greater than 7. That would be our initial pH. If I gave you an actual weak base, could you calculate its initial pH? Yes, you could, but we're not going to bother. We're just going to go, okay, we're starting up here somewhere. Now, what does the curve look like at first? Should it be all the same slope? Should it start shallow and become steep? Should it start steep and become shallow? So our slope, we have a little hill. Which way does the hill go this time? Yeah, it's a little scoopy kind of a hill, yes? So there's our little hill. And then what?
Shallow.
And then it's shallow, 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 la, 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 la. La, 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 la. And then what? Steep. Where should the middle of this vertical section be? It should be less than 7. So I think I've maybe done it now. There-ish? Yeah? Okay, there we go. Please explain to your partner why the pH at the equivalence point is less than 7. Let's just pretend if, no, yeah, you guys go ahead. If you need to come up with a weak base to use, you could use NH3 as an example. Why is the pH at the equivalence point less than 7?
Hey, good drawing. Good job. I'm not. Yeah. I had to go sleep in the middle. So why is this lower than 7? It seems like the button here and I can be replace it. You understand?
Sorry, I'm staring into space. I'm like, I just realized it looked like I was staring at you, but I'm not.
And then this one has a one. That makes a lot more sense.
This is a simple.
What can NH4 plus do? Hydrolyze. Is good? Oh. So are we all good with that? Yes. No, all weak bases hydrolyze. All weak acids hydrolyze. Yeah, those is hydrolyze. They hydrolyze because they're weak acids, because they donate protons, because the water is associated with them have the protons. Yeah? Did that answer your question? Okay. All good. Any other questions, concerns, anything? Yes. You might have to ground one of them. I think it's probably, it sounds like a very time-consuming proposition, so I don't think they'll have you do that on AP. They might get you to like finish the graph or, you know, show where the pH, the equivalence point is or something like that. Maybe, yeah. Okay, back to here. This is on page 98. The nice thing about this little thing is it actually shows you the difference between the weak acid strong base and the strong acid strong base right beside each other. So you can really, you know, if you're reviewing, you can look and you can say, oh, here's the difference. So this is weak acid, weak base, no, strong base. Eraser. Strong base versus strong acid plus strong base. Okay? And then on our next page, we go even further and we say, How does the pH point at the equivalence point change as the acid being titrated becomes weaker? So if the acid is becoming weaker, what happens to the pH at the equivalence point?
Because it's less acid, that's plus less low, that's higher. Yeah, thank you, sir. I really appreciate it.
As the acid becomes weaker, what happens to the conjugate base? The conjugate base becomes stronger. And if the conjugate base is stronger, remember at the equivalence point, the only species affecting the pH is the yes. So as the acid becomes weaker, the conjugate base becomes stronger. And since at the equivalence point, the only species affecting pH is the conjugate base, therefore the solution becomes more the basic and the pH becomes higher. Okie dokie. So you can see there's a whole bunch of curves there. Okie dokie dokie dokie. Yes.
Volume is functional.
As long as you're dealing with the same concentration, yes.
Like, the other acid, it was less here.
That's a good question. What is true of the volume required to reach the equivalence point? This is page 90, 100. This is page 100. When comparing an 0.1 molar strong acid with 0.1 molar weak acid. I guess I should also say that it's, maybe 10 milliliters, 10 milliliters. The volume and the concentration are the same for the strong acid and the weak acid. Have a little chat about that. See what you think. Which one will require the volume of NaOH? Which one will require more NaOH to reach the equivalence point? 0.1 molar, 10 milliliters or 0.1 molar strong acid, or 0.1 molar, 10 milliliters or 0.1 molar weak acid? I could have phrased that better. Which one is bigger? The amount of NaOH required to titrate 10 mils of 0.1 molar strong acid, or 10 mils of 0.1 molar weak acid to the equivalence point.
That's why blocks that is
Yes.
The same. Why is that? One's weak. Shouldn't it require less? Shouldn't it require less NaOH? What kind of arrow would we want if we're reacting a strong acid with NaOH? One-way arrow. What kind of arrow do we want if we're reacting a weak acid with NaOH? A one-way arrow. And both of these relationships are 1, 2, 1. So if the moles of if I have 10 moles of HX and I have 10 moles of HA, what moles of NaOH will I need? Thank you. So regardless of whether it's weak or strong, it is 1 to 1, and it is a one-way arrow. Why is it a one-way arrow? because the strong base pushes that reaction to completion. So we would need 10 moles and 10 moles. So the strength of the acid does not affect the moles or the volume to reach the equivalence point. Okay? Okay. We are going to skip ahead to page 106. Page 106. Choosing an indicator for the acid-base titration. Page 106. Oftentimes in an acid-base indicator, titration, an indicator is used rather than a pH meter because it's just easier if you don't need to have the whole curve shown to you, if you just need to tell where the equivalence point is. And for a strong acid, strong base titration, the pH at the equivalence point is 7, which suggests that perhaps bromthymol blue, which changes color from 6 to 7.6, would be our favorite indicator to use. Has this been our favorite indicator to use? No, we've been using phenolphthalein, which has a transition point nowhere near 7. But what do we know about what's happening here, Elliot? Yeah, a tiny amount of base, a tiny volume of base takes the pH from about 4 to about 10. Right? So does it matter if it's changing at pH 4.2 or if it's changing at pH 9? Will it still work? Will it still indicate where our equivalence point is? Yes. Can you think of a reason why we might choose phenolphthalein? Bromthymol blue is, I'm betting it's yellow and blue. Just want to figure out which form is which. So it changes from yellow to blue. And methyl orange changes from red to yellow. Nathan.
Because phenolphthalein goes because it's the fake, there's like, is it a yellow, green, blue, or a yellow that
Exactly. When we're looking at phenolphthalein, we're looking and we're saying it is pink. Oh, it's this pale pink. That's right in the middle there, okay? If we are looking at bromthymol blue, we're like, oh, is it yellowy blue? Is it yellowy green? Is it greeny yellow? Is it like, it's just that. It's easier to look for just, is it pink? Okay? Okay, are we good? So, which of the following indicators would be appropriate to choose to indicate the equivalence point of a strong base titration? So you get to pick which ones. We have, our choices are alizar in yellow, phenolphthalein, bromthymol blue, bromphenol blue, and methyl violet. Is methyl violet a good choice? No, why not? No, it's like it changes color, but it changes color like in the middle of nowhere, right? It's not at the equivalence point yet. How about bromphenol blue? Maybe. You know what I mean? Like it's kind of iffy. Right, because it's kind of, you see how we're still scooping a little bit there? So bromthymol blue, maybe. Depends on how precise your measurements are. Bromthymol blue? Yes. Phenolphthalein? Yes. Alizar in yellow? Maybe if you've got no other choice, you know. Okay. Please tell me what the difference is between an endpoint and an equivalence point.
It's all the same, but if you've done it right, they should do the same, at least in but then over time. The endpoint is one indicator. Oh, an endpoint.
Okay, endpoint. The point in titration where what? We're finishing with this, so if we sit here for 10 minutes while I wait for you. And I know Elliot and Nathan have their hands up, but I'm not going to ask them. You guys are supposed to be our best and our brightest. You should have some sort of confidence in yourselves. Well, okay. You all have imposter syndrome because do you know what our class average is? It's like 90 frickin' 5%.
I love how I do that.
We have many people in here who have 100% in this class. What with the 3% scaling? Do you know how many people got 100% in chemistry when I was in school? One girl. It was not me. You've seen my mistakes. How could I possibly ever get 100%? Oh my God. Oh, I forgot. Oh, left is right. Up is down. I forgot a negative sign. Oopsie. Pardon me? I don't know. I can't even really remember her name. Lara Ustek. And Lara Ustek, I actually, when I got to high school, I remembered the name because when I was little, I was in ballet and we'd go to these like festivals and you'd like compete in the festival. And she also took ballet, so her name was in the program. So I remembered her name. It was weird. And then there was this other time, and I don't remember this girl's name, but you know, she'd been in whatever sonatina category it was for the piano festivals. Okay. And you know, I'd see her name there all the time. I ended up working in Montreal on a work term with her. And I also ended up being at the same resort in Cuba as she was. Like, and I'm like, are you so-and-so? Did you live like in Coquitlam? And she's like, what? Why do you know? And I'm like, because your name was on the program. And you know, when you're sitting there and you're playing all those pieces, you got nothing to do but read the damn program, right? So, yeah. Okay, what's an endpoint? Stop being an imposter. I said I wasn't going to ask you guys. Yes. It's the point where the indicator changes color. You are. Would you? What is an equivalence point? You may go buy some lunch from the cafeteria. Alvin. Yes. Okay, so it's where the solution is completely neutralized, where there's no excess acid or base. You could also say where the stoichiometry of the reaction is perfectly fulfilled. Yes. Yes, I believe you could say that. Although, no, you can't. Because if you're at the equivalence point of a weak acid strong base, then H and OH are not equal because you've got that hydrolysis happening. The graphs below show the titration of a weak acid with a strong base NaOH. For each of the graphs, write down the volume of NaOH required to reach the equivalence point, the volume of NaOH required to reach the end point, and answer which of the indicators are an appropriate selection for the strong base weak acid titration. I'm sorry. You just have to go in the middle. Well, if you look, like, where's the middle? There's the middle, right? Halfway up and down. So we are done.
That bar of gray on the sheet.
I am so sorry. I really wish I had like the color for you. It makes it so much nicer. So your homework. Page 10. 103 to 105. And then we have, I still need to get you guys anhydrides, which hopefully I should have set up for tomorrow. And then we'll be done the unit. Oh, except for we do need to also do some titration calculations. So that'll be super fun. I almost want to just have the test because we're just eating time right now. Yeah. Yeah. Folks, I'm thinking of not having a second quiz for this unit, but just having the test. Are we okay with that? Think about it. Let me know tomorrow, okay? Let me know tomorrow.